Good morning, students. Oh, look,
Hello, neighbors.
we're doing something called Samesies today. Mr. Butterworth, are you doing something called Samesies today?
Samesies.
What? All right, so we've got a warm-up looking at some ways to write things as different equivalent expressions. Ooh, that's kind of cool.
I do like that.
So an equivalent expression are two things that look different but might be the same thing. So like if I've got 7n times 3n plus 1, we know this can be done with some distribution. We get 21n squared plus 7n. This would be an equivalent expression because they mean the same thing, but they're written differently.
I agree. And if we do the bottom one, we have 4w plus 2, and it's squared. So I'm going to write that down twice. 4w plus 2. And then we multiply that out. So, pew! So that's 16w squared. Pew! 8w. Pew! 8w. And 2. And 2 makes 4. And
Nice.
then you could combine those things into 16w also.
Looking at the middle one, with the math experience that I have, I know a way that we can write this that means the same thing, but I'm not going to go there right now. In a little bit, we're going to talk about ways to do something called factoring, which should be a little bit of review, but a little bit of something that's new to you. So I'm not going to go there with this one. I am going to write this as x times x minus 5 times 5, because that's another way to write this expression that means the same thing, but uses the math that we're pretty comfortable with so far to rewrite. Is that fair, Mr. Butterworth?
Yeah, I mean, if you are comfortable with factoring, that will factor into x minus 5 times x plus 5. But if you're
So,
not there, that's totally okay.
so you're saying that if we had x minus 5 times x plus 5, we'd get the same thing too?
Yes, and that's
Cool.
fine. I intentionally skipped that one because
I
you did
know.
the first one, which had distributive property, and then I went to the third one, which also had the distributive property, because the middle one was a little different.
Can I also say I really liked that you saw the squared there and you rewrote both parentheses showing that you're multiplying that whole thing by the whole thing.
I think that that's easier, and you're less likely to mistakenly write it as 16w squared plus 4.
It's true. So I guess today is really all about how can we decide when things that look different actually are the same representation of something.
That sounds great.
Ooh, which one of these does not belong with the others? That's kind of cool.
But
I,
they're all different. There's a graph, there's a table, there's an equation, and they're words.
it's true.
So what do I do?
I think we might have to kind of see what some of these, how they're connected with each other. I can do a really kind of surface level one and say that relationships A, B, and C, I can see the numbers all really clearly there. But I don't think that's what we're looking for something that's different. I think I want to look at the points that were given in relation B and see if those are connected to the points that we see on relationship A's graph. So like -6 and 5, I can't even see that. That would be somewhere up here.
That's definitely not on that graph, Mr. Carlson.
So I feel like these two might be different. I'm going to maybe just kind of put a couple more on here just to see what this is. -4, 3.
No, it's -4, -3, sir.
Ooh, thank you. Oof,
That's
that was
closer.
almost embarrassing. -2, -3. Ooh, this graph's a little bit weird, huh? 0, 5, and then 2, and then 21.
Wait, I think I know what to do. I think I should connect these things. You can't see that point you have over there, but I'm going to draw like this. I think it'll look something. I missed. I'm going to make that dot bigger. I think it looks something like that.
Cool. I think we have a name for those. I think we talked about the graphs that look like U's and called them parabola.
Yeah, I wrote it for you, buddy.
I like it. So that was
Actually,
relationship B.
A is a circle. I know that. I can see it.
Okay,
And then C, that's like the y equals mx plus b thing. So that's a line.
cool.
Oh, I got in your way. I'm sorry. Oh, I
No,
fit it.
you're good.
That was a tight
Uh,
squeeze.
then we have Zeke. He downloads a different number of apps each week. It doubles each week until he has no more storage. So,
So that
I don't know.
reminds me of the homecoming question.
Oh yeah, with the who knows homecoming king and queen, and we said that graph looked kind of like this because we're getting faster and faster as we go up.
Right. And that went like 3, 6, 12, etc.
So we call this an exponential relationship. So here's the thing. We tried to find which one doesn't belong, um, and we kind of showed how they're all different from each other.
Well, I see this word relationship, and I'm wondering if I should think of the word relation,
Hmm.
which is just a matching of like inputs and outputs or x's and y's.
So like for B, for -6, we know we have to do 5.
Yes.
For -4, we know we have to do -3.
Yes.
And in each of C and D, we could do the same type of thing with those numbers. One thing that
Yeah,
I
and
notice,
with those, I'm noticing when you put in one x value, you only get one y value, or one input value, you only get one output value.
and looking at my friend the circle, if I go over to -3, I have 2 possible outputs that I could get. The same thing at like any point except for these endpoints. We're going to have 2 answers when we put in a kind of a question. And we have mathematically an issue if we have one input that has 2 different outputs. We have a name for when that doesn't happen in relationships B, C, and D, where we have one output for every input. We call these things functions. In relationship A, we don't because we have 2 different outputs for some of these inputs.
We could say that C is the outlier
Hmm,
because for A, B, and D, there's some sort of limit to like their inputs or outputs. So for A, I can't go farther than -4 to 4.
sure.
For B, I can't go below whatever the bottom of that parabola is. So I can't go
That
below
makes
right
sense.
down here. And then same idea for the exponential function. I can't go below whatever the bottom is there. Whereas C is a line and it'll go through kind of all the X's and all the Y's.
I
I
like
don't
that.
know that that's where they wanted us to go, but I noticed that as you were talking about relations.
Sure. Okay, I think that's pretty good for a couple different ways to look at this.
And then we get to skip the next 2 slides because those we're going to talk about in class.
Oh, this is going to be an activity that we do in class. That's exciting.
It will be.
All right, so now we're looking at equivalent functions. We said the idea of a function was something that each input has one output. So there's never any question about what you're going to get if you put a number in. We have another tile company. This looks like uh, sort of some of the things we were looking at before.
Yeah, it reminds me of Miriam, but different patterns.
And I guess we want to look at all the different patterns that we observe.
So the first thing I notice is in the corners.
Mm-hmm.
The corners, like that's a 1 by 1 square, a 2 by 2 square, a 3 by 3 square. So the design number matches the corners.
Yeah, that makes sense to me. The second thing I notice is the middle. Here we have a 3 by 3 middle. This one is a 5 by 5 middle. And this one, 1, 2, 3, 4, 5, 6, 7,
I was
is a
hoping it was
7
7.
by 7 middle. So that kind of reminds me of the pattern we had before, where I think we had the same numbers in there.
Should we look at the total number of tiles also?
I think so.
So we have 9 and then 4, so we have 13 in the first one. And then 25 and 16 is 41. And then 49 and 36 is 79, 85.
Oh, that's for the total number of gray tiles.
Yes.
Okay, I thought you were doing total number of tiles overall.
Oh,
So I will do the total number of tiles overall
I was thinking gray.
because we're going from 5 by 5, 9 by 9, and then 13 by 13 for the total tiles.
So I'm seeing the odd pattern of the 3 by 3, 5 by 5, 7 by 7, and then the skipping odd pattern of 5 by 5, 9 by 9, 13 by 13.
Yeah, so we're kind of doing a bunch of different things that we see here.
Beautiful.
Cool. All right, numerically organize the pattern. Hey, those are kind of some of the things that we looked at before. We didn't do the number of white tiles in any of our patterns that we noticed.
We did, and I thought about it when you started talking about total, but then I didn't want to. But the first one says it's three sets of 4, so that's 12.
Okay.
And then
You get
the number
4
of gray tiles
sets.
was 9 and 4, which is 13.
Yep.
And the total number was 25, because that was the 5 by 5 you talked about.
Yeah. And then the second one, we've got sets of 10 white tiles, so that's 40. And we've got 25 plus 16 is going to be 41, giving us 81 total.
And then the last one you said was what was it? 13 by 13.
13.
There are 169 of those. And we knew, I'm going to cheat and look back. We knew that there were 85 gray ones. 85 gray ones. And then there are, what the heck's going on there? 1, 2, 3, 4, 5,
Should be
6,
84, I think.
7. 7 by 3, so it's 21. Yeah. Okay.
I'm just going to clarify your handwriting because it looks like 49 down below.
Yeah, it does. I apologize. I got a little sloppy there.
That's okay. And then we got to do some predicting of things and try to make sense of what's going on. To me, I think the easiest pattern for me to see are the patterns at the bottom, because that's 5 by 5, 9 by 9, 13 by 13. We're adding 4 each time to our sides. So this would be 17 by 17, which should be 389?
289, right?
289, yeah. That would be 21 by 21, which is 441. And then 25 by 25 is 625. That's a lot.
True. And let's do the white ones. I feel like are going to be easier, because for the white ones in design 1, it was 4 sets
Of 1 by 3.
of 1 by 3. And then for design 2, it was 4 sets of 2 by 5. For design 3, it was 4 sets
3 by
of
7.
3. I wrote sects twice. I'm apparently having issues with words. Sets.
That's
There we
chill.
go. Sets. There we go. So I'm noticing that these numbers match these numbers.
I agree.
So for like the fourth one, there'll be 4 sets. 4 of 4 by.
And these ones are going up by 2.
So 4 by 9.
Okay, so that's 108 total. And that's for white tiles?
Yes.
Okay. And then for the fifth one, we'd have 4 sets of 5 by 11, because we're increasing by 1 and then increasing by 2.
Yes.
So that would be 220.
Is it just double plus 1?
You mean plus 1, double plus 1?
Like if I take 1 by 3, if I double 1 and add 1, I get 3. If I double 2 and add 1, I get 5. If I double 3 and add 1, I get 7.
Oh, so yeah, that makes sense.
Because I'm trying to predict, because although you wrote that number under the 7, that
Oh,
was
that would have been
5
5.
number.
And these numbers are not accurate either because I went up by 4, assuming that those were 5 and 6.
Oh, I didn't catch that one. That was, yeah. So for 7, it'd be 4 of 7 by double plus 1, so 15.
Cool. So that's
And
7
that,
times 60 is 420.
yes, I had to process what you just did. So what he just did is he multiplied 15 by 4 and then multiplied by 7 because that made more sense in his brain. Threw me for a loop. I was going to do 7 times 15 and then times 4. But I like what you did. That was easier math. And then
I noticed the bottom then would be quadruple plus 1, kind of like we're doubling plus 1 to get there.
so 2 times 4 is 8 plus 1 is 9. 3 times 4 is 12 plus 1 is 13. Like it. So for 10, it's 4 sets of 10 by double plus 1, 21.
Cool. That one's easier to figure out.
Okay. So now we need to fill in the numbers. So you said for 7, you said it was 420.
Yep.
And then that's 210 and 4 of those, so that's 840.
I agree. And then for 29 squared, that's 781?
I don't know what
No,
29 squared is. 30 squared is
it's
900
900.
though. So it's got to be higher than that. I'm going to assume you're calculating it, but maybe not. I'm too lazy to do this. I'm just going to grab a calculator. 29 squared. 29 times 29. 841.
841. Oh, I was so close.
That's beyond the squares that I know. And then you're going to need 41 squared.
And then 41 squared.
1681.
There's something kind of interesting happening here.
What's interesting?
That 1681 is made up of 841 and 840. 841 is made up of 421 and 420.
Oh, there's one different?
Did we do number 4 wrong? Because that doesn't make sense with these numbers.
I'm going to blame you. I just believed you. So we said it was 4 sets of 4 by 9.
36 is not, it's 144. There we go. Yep, that's me. I did 36 times 4 and
believed
got
you when you said
108.
108 and didn't even question you. I should have questioned you.
And then we got 145 for gray tiles. So that's kind of cool. That was kind of neat how that happened.
Yeah. So what you're saying is we figured out the white tile pattern where it was 4 times whatever the n value was times 2n plus 1.
Right.
That was for the white. And for the gray,
it was that plus 1.
Plus 1. So this is 4n, 2n plus 1, if we make this an n column. And then this is 4n, 2n plus 1 plus 1.
And then the total number, the way that we kind of did this was say that this was, each side was 4n plus 1 because we quadrupled and then added 1. And then we multiplied that by itself. So another 4n plus 1.
Got it. I think we did some stuff.
I think we did.
Although it says, don't worry about the last column for now. You will determine an expression for these two.
Yeah, I think we may have done some stuff early that we didn't have to do yet. But let's see. Oh, these are answering the questions that we just kind of figured out.
I I think we just did all of this, so we're good.
I think we just did all of this too.
I think the middle one that they can figure out based on what we did.
I like it.
Now we've
All
got
right.
Tonya and Alex came up with different expressions to represent the number of gray tiles in each pattern. Their expressions are shown. Neither of those is what we did.
I noticed that this is the pattern that we said for the total. And 4n times 2n plus 1 is the pattern that we said for the white tiles.
Oh, that's true. So total minus white, so that's the gray.
That
I
makes
like it.
sense. I don't recognize any patterns in Tanya's. But what if we multiplied these together and saw if this was the same thing?
So that would be 4n squared plus another 4n squared plus 2n and 2n, and then plus 1.
Okay, so that would be 8n squared plus 4n plus 1.
I'm going to multiply this one out. 16n squared, that's going to be 8n and 8n, so that's going to be 16n plus 1 minus, don't forget parentheses, 8n squared minus 4n.
Where's the 16n coming from? You think you
Right.
doubled?
Oh, that should be 8n. Sorry. Thank you. I thought you were talking about that. See, this is why you should write down your work. Woo! So then we get 4n, like you said, plus 1, and 8n squared. So those are the same. And then we put graphs over here of Tanya's and Alex's. Those look like they're the same graph.
They do. And I noticed that if I were to combine Alex's or Tanya's like terms, 16 squared minus 8n squared gives me the same thing Tanya had for 8n squared.
Mm-hmm.
8n minus 4n gives me the 4n. Plus 1 gives me plus 1. So algebraically, they look the same after we play with them. And graphically, they look the same. So I would say that these are both the same and correct expressions.
Yes, I agree. I just added, I had put a minus in front of the 4n. I changed that to a plus because that's what it should have been. I like automatically distributed in my brain, but
Yep.
left parentheses. So that was mathematically incorrect. But I agree. Those look the same.
All right. So there are some patterns in the sequence. Is this kind of what we just did?
Yes.
This is showing the steps that we just did in a couple different ways. One is looking at the white tiles plus the gray tiles, and then adding those pieces up, and the other is looking at the total tiles just and kind of multiplying that out, which we've done all of this on previous slides.
And now we are done. That is it. The rest of the stuff is extension work. You are welcome to work on it and ask for our help.
Would
But
this
you
be a
do
good
not,
thing to do in class time if you're finding that you're feeling really comfortable with stuff?
yes, yes. If we have some time in class to do some work and you want to work on these, by all means, go for it.
I like it.